Today we are gonna use the Matlab Simulink environment to model the whole transmitter and receiver chains of an FMCW radar using phased array and antenna toolboxes. Let us first look at the radar and the target's position. The radar platform is placed at the origin of the coordinates, and three targets are placed at the typical range of about 15.5 meters away from the radar. There are two vibrating targets, namely T1 and T2, which are vibrating with different magnitudes and frequencies to mimic the behavior of a human chest wall, which is vibrating due to breathing and heartbeats. Thus, the results from this simulation can be used further to design and implement an FMCW radar for vital signs detection. Now we are going to a step-by-step explanation of the model from the transmitter to the receiver. First of all, for the purpose of the simulation, we are using op chips, meaning that the generator generates chips with a positive frequency time slope, and the duration of each chip is 64 microseconds and the bandwidth is 100 megahertz, which means that the output sample rate of the FMCW generator is 100 megasample per second. The FMCW signal then goes to the hardware section, which adds a phase node in order to investigate the range correlation effect in the system. The phase node added signal then goes into a radiator, which converts the signal to an electromagnetic field by considering the antenna pattern and the polarization. The channel calculates the two-way path loss and the propagation delay between the targets and the radar. The wave is reflected off the targets and collected by a collector at the receiver, which also includes the antenna polarization. Then the receiver takes the echo signal and adds a thermal loss to it and mixes it with the transmit chips in order to obtain a bit signal which contains information about the target's ranges and as well as their vibration frequencies. Then the IQ imbalance block adds the IQ mismatches, and then the sample rate of the signal is reduced by a factor of 50 by the ADC sub block. And then the downsampled signal goes to the baseband for further signal processing. Now let us run the model to see the signal attributes at different points. Look at the spectrogram of the FMCW generator output. You could see that the chip duration is exactly 64 microseconds with the bandwidth of 100 megahertz. After selecting the desired range, we can plot the complex samples on a complex plane. So the points shows us an arc of a circle which has a center shifted from the origin of the plane. That center shift can be shown theoretically when there are two vibrating objects which are modulating the phase non-linearly. Points are not shaping a straight line, rather than they are scattered around the arc of the circle because of the phase nodes we have added, and as well as the AWGN and the IQ imbalance effects. So let us look at the time domain representation of the phase after unwrapping. You could see the phase variation after phase unwrapping of the desired range being, and initially the phase has a transition because of the delays in the path. The phase is the summation of the two sinusoids. In ideal, the largest period of the phase is for the first object, and the small high frequencies in the phase are for the second target. But the phase doesn't have a clean signal, distorted by the AWGN and the phase nodes and the IQ imbalances, as we said before. Let us look at the phase spectrum. The phase spectrum after the transition time, we will see that it has lots of harmonics because of the IQ imbalance and as well as the stationary relativity. The first two peaks in the phase spectrum are corresponding to the fundamental and the second harmonics of the first target. But if we are taking those peaks as the frequencies of the two targets, the second harmonic of the first target will be considered as the frequency of the second target. In order to reduce the confusion for estimating the frequencies, a more stable and robust algorithm is used, and you could see the output of the algorithm in the figure. With this Simulink model, we can investigate the effects of the phase noise, thermal noise, IQ imbalance, and stationary target on the system performance. These are helpful to obtain the circuit and system parameters for designing and implementing the radar for vital signs detection. Thank you for watching the video.